Thank you very much. I'll try going to the next slide, and so you can both see that it works and see what the talk will be about. So I thank, of course, the organizers for inviting me and for maintaining this conference. I look forward to seeing all of you in a year, but in the meantime, I'm very happy to be talking about this subject today. So I'll be talking only about linear groups for this afternoon. And it's perhaps fitting that our conference starts with mentioning Harish Chandra's work. And since the main object for today will be the tempered duo of a reductive group, of course, much has been said by Harish Chandra himself, especially the determination of the Blancharel measure. And as Langlands wrote somewhere, he was, of course, the chief engineer of the theory, but not the exclusive architect. And his work was completed by others. And some of what we'll need today includes the classification of irreducible tempered representations by Knapp and Zuckerman, using limits of discrete series to study the reducibility of induced representations, and the R group. And in turn, this makes it possible to give information on the Fell topology of the tempered dual, which will play an important role here. So just, I won't be giving many definitions to start with, but I'll just recall how this looks like, how the tempered dual looks like for Harish Chandra's and everybody's favorite reductive group. So we have this two kind of series of representations, the discrete series, which exists for SL2 but not for other groups. For real groups, the discrete series can be empty. And you have for SL2 two series of representations induced from a minimal parabolic subgroup. So a series of spherical representations. I drew it with a big endpoint, but it's really a closed half-line, right? And the non-spherical principal series is an open half-line with two endpoints. So the tempered dual is usually not Hausdorff, and this will play an important role in orthodox. Well, with Harish Chandra's work being a thing of such beauty and power, it's been incorporated into our thinking for decades, and the subject has been taking on a rather algebraic flavor these past years. But it's easy to forget that 50 years ago, the hard analysis on the Riemannian symmetric space G mod K used to play a prominent role, especially the analysis at infinity, the geometry of G mod K at infinity and the asymptotic behavior of eigenfunctions of the Laplacian and things like that. Today, we'll be looking at something rather different than the behavior at infinity, because we'll be zooming in on a neighborhood of the origin of G mod K. Of course, this space is topologically trivial. It's diffeomorphic with the tangent space at the identity coset. So topologically, G mod K is rather trivial. But the isometries of G mod K are rather different from the isometries of the tangent space. If you look at the group of affine transformations of this P, whose linear part is in G, you obtain a group which has the same dimension as G, and contains a maximum compact subgroup, but also contains all translations of this P space, and therefore is, of course, not reductive, and in many respects simpler than the initial group. So this group is just K cross P. Oops, so as a set, and it has the semi-direct product law as follows. you use the adjoint action of K on P, which is P scalar. So C2 plus C1. And so this group has the same dimension as G, but a much simpler structure. And of course, we'll be talking much about the fact that its representation theory ought to be significantly simpler than that of G. Now, the relationship between G and G0 is of a famous kind in physics. I was telling you earlier that this Riemannian symmetric space is diffeomorphic with P thanks to this Cartan decomposition, diffeomorphism to phi. Now, if you zoom in on the neighborhood of the origin, you can build a family of groups which act on spaces with smaller and smaller curvature obtained by rescaling the metric for each parameter t here. You can build a group that acts on a space on rather smaller curvature and also has underlying set k cross p, but a group law that is a bit different, and it's not difficult to check that this gt has, since it has the same underlying set as G0, it's meaningful to look at the product in GT and to see whether it goes to the product in G0, and that is the case. So GT goes in a sense to G0 as T goes to 0.
Alexander, I have difficulty seeing what you're writing at the bottom of the screen.
Oh, sorry, I'll try to avoid writing at the bottom on the screen then. If I write something here, is it all right?
That's fine.
Okay, thank you. So I'll try to avoid the last lines. Thank you. Well, I said that this kind of deformation was famous in physics when you have a small parameter that can go to a limiting value. It can change the isomorphism class of the group. And a famous example of this kind is when you have the Poincaré group of special relativity with the speed of light embedded into the definition. And when the speed of light goes to infinity, you can build the Galilei group of not special relativity, classical inertial changes. And it's not isomorphic to the Poincaré group, but is a what physicists call a contraction of it. So the relationship between these two groups is fairly simple. And it's classical in physics to wonder, because of the interpretation of unitary representation as in quantum mechanics, about the relationship between the representation theories of these G and the group G0. As I was saying, it ought to be very different. It's well known that in physics, the interesting representations of the Poincaré group somehow vanish as you perform the contraction to the contracted group. So usually there ought not to be a simple relationship between the representation theories of G and G0. It's perhaps expected that they should be different, because G0 is very simple. You see, it contains the abelian subgroup P as a normal subgroup, and the quotient is just K. So if you have a representation of G, of K, sorry, you can build a representation of G0 just by factoring through the quotient map. So you go in G0 mod P, and you just choose pi of K. So there is a family of finite dimensional representations of G0, which are just the representations of K trivially extended to G0. So it has very simple representations, which are nothing like the representations of G, which are rich and Interesting. However, if you look at pictures for the tempered dual of the reductive group and the unitary dual of the contracted group, you start to think that the parameters that are needed to describe the representations are not very different. The topologies are obviously different. Here you have a reductive case with an infinite number of connected components in the tempered dual. And here is the corresponding Cartan motion group. It's just the group of the Euclidean motions of the plane. And it also has a countable family of simple representations, which I was telling you about just today, but only two connected components because of various incidence relations on the other series of representations. So the duals cannot be the same, but they look pretty much the same. And in the early 1970s, George Mackey, who had, of course, single-handedly determined the unitary dual of this G0, started looking at simple examples and saw that the parameters did look very much alike in general. And he said, perhaps there should exist a natural bijection between the dual spaces. And this idea was deemed perhaps over-enthusiastic at the time, and Mackey was somehow prophet that wasn't heard at the time. And the idea that this might be possible almost died out in the 70s and 80s until non-commutative geometry and sister algebras rescued it. I've been talking about the topology of these tempered duals. So from the point of view of non-commutative geometry, these occur as the spectra of the reduced sister algebras of both groups. And Alan Cohn and Nigel Hickson pointed out that the idea that these two dual spaces could share some characteristics fitted well with the Cohn-Kasparov conjecture, which predicted that the sister algebras had, in a very precise sense, the same K-theories. So the connection was not made extremely precise at the time, except as a natural problem. And for a while, for decades, the high priest of the subject remained Nigel, who is listening to us, I think. And so in the early 2000s, Nigel constructed such a correspondence and verified that it did induce the bound Cohn-Kasparov isomorphism, but for complex reductive groups. And about 5 years ago, I came into the subject by a somewhat unexpected route, and it appeared that such a bijection indeed exists and has interesting properties and leads to many things we would like to study. So for the rest of my talk, I'll be telling you about this bijection at the level of tempered representations only. So I'll start by describing it, and afterwards I'll give you some thoughts about realizing it in various ways. Perhaps some of you have already heard me tell this, so I shift the focus for today to constructing it from things that are obviously shared by the two groups G0 and G, and characteristics of the duals that somehow pop up to the eye as soon as you look at them. And before that, I'll describe the unitary dual of G0 and tell you why it's so simple. As I said, it's because there is this abelian normal subgroup P, and there is Mackey's theory from the 1940s, which allows us to build the representations from the action of K on the dual of P, or equivalently on the unitary representations of P and So if you start from the action and an orbit, you can look not only at the orbit, but at information concerning the stabilizers of points in the dual. So if you have the point in the P star in the algebraic dual, I'll be calling K chi the stabilizer of it in K. And you can start from a datum consisting of this chi and the representation of the stabilizer. And Mackey constructs representations of G0 in 3 steps. The first step is to use the centralizer of chi for the coadjoint action. So this centralizer chi for coadjoint action. Obviously, it contains the stabilizer k chi, and it contains all translations of P, since P acts trivially on P star. And from the datum I was telling you about, you can build a representation of this centralizer. You see, if you have a representation of the compact stabilizer, you can have k chi act like it, through it, and you can have P act through the character you're starting from, because the centralizer is the semi-direct product. It gives you a representation of the centralizer, and you can induce to G0. This is really one of the most simple examples of induced representations for groups that are neither compact nor abelian. And Mackey saw in the 1940s that you always obtain an irreducible representation in that way, and that every irreducible representation of G0 is obtained in that way. So you have under your eyes the construction of all unitary representations of G0. So as I was saying, this contains a copy of k hats here. So it corresponds to starting from the orbits that is just the singleton located at the origin. And then you just look at the representation of k and extend it trivially to G0. But when you start from a non-zero chi for SL2R, it means that you are looking at a radius for an orbit of SO2 on R2. And depending on the character of the stabilizer k chi, which here has 2 elements that you use, you can build either a spherical infinite dimensional representation or a non-spherical. So it's really very simple. So is everything clear so far? Yes, please feel free to interrupt if you have questions. So now you probably all know at least much more than I do about the tempered dual, and you know there is something that is shared by both duals. It's the existence of kind of a fine parameter of affine parameters for both duals, of the possibility of renormalizing some parameters. You see, in this picture for G0, you can of course dilate the parameters chi and obtain different representations. So there is a renormalization map. Sorry for a Frenchman, that is a bit of a tongue twister. There is a way to renormalize a representation of G0 to go to another representation of G0. You can just take the character and multiply it by a constant, and you obtain a way to wander around along a half line in the unitary dual of G0. So there is a rescaling map in this G0 hat. For G, it's well known that there also is a way to renormalize representations, that is in renormalizing the imaginary part of the infinitesimal character. You see, from Harish Chandra's work, you know that you can realize any tempered representation as a submodule of one induced from discrete series. I'll be using a cuspidal parabolic subgroup and the Langlands decomposition of a Levy subgroup in which M is generated by compact subgroups, and A is the split component. And then you can write pi as a submodule of representation induced from a discrete series representation of this M and from a character of the split component. And then the characters of the split component do form a vector space. So you can take this chi parameter and renormalize it just as we did for G0. And you obtain a way, rescaling map from the tempered dual of G to itself. So there are really natural structures for renormalizing representations in both fields. And I'll construct the Mackey bijection by requesting that it commute with these rescaling maps. So if it does commute with the rescaling map, it must send a fixed point under rescaling for G0 here to the fixed point under rescaling for G here. So what are those? For G0, it's the copy of K hat that I was telling you about, a countable family of finite dimensional representations. And for G, it's the representations that occur in some induced, of one induced from discrete series, but which has the continuous parameter here trivial, so that it's not changed under normalization. This is equivalent to requesting that the representation you start from has real infinitesimal character. So the class of rescaling invariant representations is the class of tempered irreducible representations with real infinitesimal character. I'll be denoting it by this symbol. So what we are looking for, at least for the rescaling invariant representations, is a bijection between K hats and this class of real infinitesimal character representations. And it turns out that such a bijection is buried somewhere in the work of David Vaughan from the 1970s and 80s. The bijection is obtained by looking at lowest K types. So just a few words on lowest K types. Vaughan introduced a way to measure somehow the length of a K type by using just the length of the highest weight in a sense. So if K is connected and you fix a maximal torus, you can start from a representation once you fix an ordering and decide that its length is just the length of a shifted version of the highest weight. In a way, this doesn't depend on the choices you made. And because the highest weights form a kind of lattice in the dual of, so it's T hat, in the dual of T, there is only a finite number of representations that have length less than any fixed number. And so if you start from a representation of G and look at its restriction to K, it will decompose discretely. And among those, the representations of K that occur, there is only a finite number of representations that will have this norm lowest among all K sub-representations. So we'll use that because Vaughan proved, and it's somehow deep results, that if you start from a representation in our class of real infinitesimal character representation, then it has a unique lowest K type. So you can extract from it one element of K hat. And it is enough to know which representation of real infinitesimal character you've started from. Furthermore, every K type occurs in this way. So by taking the lowest K type of any representation in the class of representations with real infinitesimal character, you obtain a bijection with K hat, just as we were hoping for. And it's the only way to write down a bijection between K hat and this class that respects lowest K types, of course. So any Mackey-like bijection that commutes with rescaling maps and preserves lowest k-types must be this Vaughan bijection between k-hat and the class I was telling you about. Now we only have to try to build the rest of the bijection. We've built the somehow core of the bijection, and we need to see how the Mackey construction of all other representations can be used to build representations of G. And perhaps we can just do things naively. You see, I'm just displaying again the slide from earlier. We started from an element of P star and the representation of the stabilizer, and then considered the centralizer in G0 for the coadjuvant action, and then built something from that and induced to G0. We can do the same thing for G. You start with the same datum, and you look at the centralizer of the character here in G for the coadjuvant action. You obtain a subgroup of G, and it does contain this compact little group as a maximal compact subgroup. Our next task, if we are to follow Mackey's recipe, is to build a representation of the stabilizer, L-chi, from that. And with Vaughan's theorem in hand, it's possible to do so. You see, the group L-chi admits K-chi as a maximal compact subgroup. And we've seen that from mu, you can build the representation of L-chi with real infinitesimal character automatically using lowest K-type theory and Vaughan's work. And on the other hand, you can use the continuous parameter chi to define a representation of L-chi, because you have this Langlands decomposition as a direct product in which A is contained in the exponential of P. And so you can use chi to define the character of A chi and then of L chi. So from the Mackey data, you just have this centralizer.
I'm sorry.
Stabilizer, yes?
Excuse me. I must be missing something. Can you return to the previous slide?
Yes.
No, I don't see how G acts on P star.
G doesn't act on P star.
G doesn't act on P star. So what is L-chi?
Sorry, it acts on G star, and you can you can view chi as an element of G star by just making it equal to 0 on the orthogonal.
Thank you. Okay, thank you.
Right, so the last step in Mackey's program was to induce to G. And here it's not a good idea, you know, that usually we need parabolic subgroups to induce from in temporal representation theory. And the group L-chi is not a parabolic subgroup, but fortunately it's a Levy subgroup. And it has an amusing relationship with the centralizer we induced from earlier, because this L-chi has smaller dimension than the stabilizer we induced from earlier. But if you look at any parabolic subgroup with Levy factor L-chi, it will have the same dimension as the earlier stabilizer and contract on it if you do the contraction I was describing at the beginning. So you can just inflate our representation sigma to the parabolic and induce to G and look at the result. It's not obvious at all that it should be an irreducible representation, for instance. But if you open Harris-Chandler's work and the Knapp-Zuckerman classification and all that, you do see that you will obtain an irreducible representation. Furthermore, the representation you obtain depends only on the class of the induced representation of G0 we built earlier. And if you use the Knapp-Zuckerman classification, you can see that, in fact, everything in the tempered dual of G is obtained in this way. So we have built the Mackey bijection between the unitary dual of G0 and the tempered dual of G here by first identifying the image of K hat thanks to our structural requirements, and then imitating Mackey's recipe. Now, this will be a bit of commercial leaflets, if you allow me to say so, because this bijection, well, it's obviously nice. I mean, the formula is simple once you've this Vaughan map in hand, and it does have nice properties. Of course, it does commute with the rescaling map by definition. It also preserves the lowest K types for all representations, not just for the class I built this from earlier. And it also has very nice topological properties. I won't be describing this today because I want to talk about something different, but it's very nice topologically. It's a piecewise homeomorphism, and it's continuous in one sense, in one direction, although it cannot be continuous in the other direction because we saw that the topologies on both fields are different. Each of these sentences has a proof of its own that would take us to different subjects, but these seem interesting to me, and especially they seem related to the recent work of Nigel and Angel Roman, who I think is also listening to us, which puts somehow shows how the rescaling maps I started from earlier are important in that subject. It would also be very interesting to describe the extension to the admissible dual, and it comes with its own set of problems. The people I should quote here are also listening to us. As you see, the high priest is still Nigel, but there are also many results due to Ayal Subag, and a general framework for studying deformations of representations in a much broader setting due to Joseph Bernstein, Nigel, and Ayal. I won't be telling you about this, but there are phenomena here that are very intriguing to me, especially given what I'm going to tell you about now. Because you see, I told you that G and G0 were related by a continuous family, GT. And then it completely disappeared from the construction I told you about, even though the very existence of the bijection was motivated by the existence of the family and the fact that in physics, it's a classical problem to try to start with a representation of G and deform it into a representation of G0 if that is at all possible, and that there are settings in which it is not possible to do such a thing. So for the Mackey problem, you can build a family of representation out of any representation of G. You see, the groups GT for T non-zero are all isomorphic to G. So you can try to build, you can actually build a family of representations of GT for T non-zero. And it's natural to hope that as T goes to zero, the representations you have built do converge in some unspecified meaning to the representation of G0 that corresponds to pi in the Mackey bijection. But of course, there are many problems. They do not act on the same space. It depends on the geometrical realization you choose. And it's not obvious that there are topologies for which you can study the convergence. Yet, if you can embed all this family of representation into a fixed space, you know, the groups GT and G are all isomorphic. And so by Shaw's lemma, you will have an almost uniquely determined map from here to there. And it's natural to try to determine if there's a convergence, but you need to see the topology. So I'm going to spend the last 25 minutes describing to you the ideas that are needed to realize, to implement this program. And I'll start by giving you two simple examples in which the most important ideas appear. And this will be for an arbitrary group, not quite arbitrary because I have to assume that it's connected in semi-simple and that it has a discrete series, but not just an example. Any group with discrete series and it's connected to semi-simple. You remember the discrete series representations do have real infinitesimal character. They are in the class we talked about. And the representation of G0 that corresponds to it is just a representation of K, its lowest K type. So what we want to do is see whether we can deform pi onto its lowest K type by a kind of procedure. For that, it's very useful that there is a realization as a space of sections of a finite dimensional bundle of G mod K, because G mod K is the same for G, for GT, and for G0. So let me recall this Atiyah Schmidt Professor realization. You start with a finite dimensional K module, not exactly the lowest K type mu, because you need spinors, you see, to build a Dirac equation, but a module that you can canonically construct from it and that contains mu exactly once. With that, you can form a finite dimensional bundle over G mod K that is equipped with a, a spinor structure and the Riemannian metric, and so you can build the Dirac operator. And then look at the L-square kernel. It's a very famous result of Atiyah and Schmidt, that thus you obtain a representation of G with class pi, the discrete series you were starting from. One thing that is extremely important for our purposes, that is hidden somewhat delicately inside Atiyah and Schmidt's proof, is that when you look at the solutions of this Dirac equation, they should explore the fiber, but they do not explore the fiber in its entirety. They explore only a sub-bundle that corresponds to the representation of K that gives to the lowest K type. So in a sense, the lowest K type pops up in that way in the Atiyah-Schmidt construction. It's the subspace of the fiber that is spanned by the value of the solutions at any point at the origin. And now, there is a way to compare this to what happens for GT. You know, we can transfer everything to P, which is diffeomorphic both to G mod K and to GT mod K. So you have a family of actions on P, a family of metrics, a family of differential operators acting on sections. And since P is topologically trivial, you can trivialize all the bundles and obtain a family of operators acting on a fixed space. To obtain a space of functions rather than sections, you need to pass through the square of the Dirac operator, but I won't be giving details about that. The point is, you can build a discrete series representation of GT as a subspace of a fixed space. Here. By what I was telling you earlier, there should be, so Eric, you said you couldn't see what I was writing at the bottom. So I will take this here. So you have the equation for t equals 1. You have the equation for arbitrary t. And I said that there is an almost uniquely determined evolution operator from here to there, thanks to the fact that all GT are isomorphic. So what does it look like? It's fairly easy to identify. It's just a dilation. The relationship between G mod K and GT mod K is just the dilation. And when you project everything to P and you zoom in on a neighborhood of the origin, you see that the metrics are intertwined by the dilation, and that the Dirac operators are conjugate. So the space of solutions for the initial equation just go to the space of maps that you obtain by zooming in on the solution at the initial moment to a neighborhood of the origin. And therefore, what happens when you contract, when you zoom in on the neighborhood of the origin for a function? Well, it starts looking like a constant, just the constant given by its value at the origin here. Of course, the convergence is not for the L-square topology. When you zoom in on a function and it goes to a constant, it's for the topology of uniform convergence on compact subsets. But it does go, for this topology, it does go to the value at the origin. And the value at the origin is a member of a space of which I was telling you that it carries the lowest k-type. And so eventually, starting from an element of H of the space of L-square solutions, you obtain an element of the carrier space for the lowest k-type. So we have succeeded in building the lowest k-type by a deformation procedure out of a discrete series representation. So I see time is running. So let's just take away that it's possible to contract things if you find a nice enough geometrical realization to compare G and GT, if you use a topology that's appropriate to the situation, and well, there are other problems. I'll now say a word about somehow the opposite situation, the spherical principal series, for which we can also build a space of functions on G mod K. This is, in a sense, due to Harish-Chandra, but has been expanded upon by Helgason in a very beautiful way. There are analogs on G mod K of the plane waves of Fourier analysis. These are called Helgason waves. I'm perhaps one of the only people to call it like that. But these are functions that have phase lines that are horocycles in G. Here I only drew the argument, not the modulus. The modulus goes to infinity in one direction and to 0 in the other direction. But there are plane waves attached to every regular point, and you can rotate them to obtain a family of plane waves propagating in all possible directions in G mod K. And when you sum all these up on the boundary, on the all possible directions, what you obtain is the spherical function of Harish-Chandra, which serves as a matrix element for the spherical principal series representation. So, in fact, using these Helgason waves, you can build a space of genuine functions on G mod K that carries any spherical principal series representation. The advantage of this over, say, the compact picture that you can have more usually the principal series representation is just a compact picture. When you use these Helgason waves, you can build a space of functions on P. If you use exponential coordinates, the Helgason waves look like this. This time I drew the modulus. They are waves with somehow curvy wavefronts. And so we can try to take up the strategy of earlier and zoom in on the neighborhood of the origin. Since these are eigenfunctions of the Laplace operator, and the Laplace operator is related to the metric, you could expect that zooming in will build you wave for the group GT. The problem is that if you zoom in, the wave fronts will indeed be less curved, but they will also spread apart. And if you want to build something that looks like the initial wave, but with evenly spaced wavefronts, you need to renormalize the frequency. You need to replace chi by chi over t if you wish the waves to look like one another. But if you do this, if you zoom and at the same time renormalize the imaginary part of the infinitesimal character, you will find that the waves do start looking like Euclidean plane waves. And eventually you obtain the combination of all plane waves propagating in various directions and with a fixed spatial frequency. And that is how you realize the spherical representations of G0. So here again, you have a space of functions that you need to equip with, that you embed into the space of smooth functions on P, this times with values in C, and using the topology of uniform convergence on compact subsets and of all derivatives.
Can I ask something?
Yes, yes, I am.
Can you please repeat what's the advantage, say, if you use the compact picture, what's the advantage of this Helgeson's wave?
Oh, you're perhaps one step ahead, Ayal, because you can do this in the compact picture for the spherical principal series.
Yes.
Right, but in that, if you do that, the relationship between the discrete series and the fact that the only additional idea is this renormalization of the imaginary part of the infinitesimal character is perhaps less clear. So it's not necessary to use this space of functions of P on P. It just makes it easier to see why what the relationship is with the earlier construction.
Okay, thank you.
Thanks. Now, in the two examples, we found a space in which to embed everything that was not a Hilbert space, it was a Fréchet space with its special topology. And we found subspaces, the actions of GT on these subspaces, and almost automatically determine evolution operators from one space to the other, almost automatically determined if you ask about this, if you ask that it intertwines representations with this renormalizing condition. I won't go into details. But you can hope that everything converges in as much as the vectors go to some limits, and the space of all limits builds you something, and the operators go to some operators, so that you end up with a representation of G0. And of course, you can hope that you obtain in this way a representation of G0 that does correspond to the initial representation in the mathematical. In fact, it's not easy to do that, and I must say that it took me a long time. That the two examples I was telling about are essentially in my thesis from 4 years ago, and I finished building a contraction of all these things about 2 years ago. It's just been published. I'll be very sketchy because I have only 10 minutes left, but I'll describe the main steps for the general procedure and the main difficulties. All of the important ideas already appear in the examples I was telling you about. The first thing is, Ayal was asking about the compact picture. He's right to ask about that because the spherical principal series in the compact picture appears as a kind of model for every generalized principal series representation. Every representation induced from a limit of discrete series of Hospital-Levy subgroup. So if you translate what I've done for the G mod K to that setting, you obtain an idea of how things can work for a general representation, provided you can contract the supplementary ingredient, which is usually not a discrete series representation, but a representation of the compactly generated part of the Levy subgroup with real infinitesimal character. So in a sense, if you use the ideas of the second example, if you can generalize my first example to all representations with real infinitesimal character, you will be able to contract everything. Of course, there are many details. So the two steps, what I've just described to you is the second. It's easier than the first, although it's quite technical because, you know, the Levy subgroups are not connected even when G is connected, and there are many details to check. But where new ideas are needed, and where I spend the last 8 minutes, is for the real infinitesimal character representation. Because there you cannot use G mod K always. And you must use cohomological induction, which usually is described rather algebraically rather than analytically. Since I'm not very at ease with algebraic methods, it took me a long time to translate the cohomological constructions into analysis using especially the work of Wong on the maximum globalizations conjectures, and to see that it's possible to realize any representation in the class of real infinitesimal character as a space of sections or Dolbeault cohomology for an elliptic quadrant orbit. But the details are somewhat painful because you can use a bundle over an elliptic quadrant orbit, G mod L, where the Levy subgroup you start from is pleasant because it's quasi-split, but you induce from a representation that is not finite dimensional as we did for G mod K. You must use cohomological induction with an infinite dimensional representation. But you can actually do that. You can build an infinite rank bundle over G mod L. You have to twist things by a character of L to build things. But Schmidt, Wong, and Zuckerman identified a precise Dolbeault cohomology space for this bundle V sharp that carries the representation we are wishing to contract on its lowest scale, right? So what we need to see is whether G mod L lends itself to the kind of zooming in that we did for the other representations. And there is an old theorem of Mostov that makes it possible. The theorem is as follows. G mod L is not a vector space. It's far from being a vector space. But there is a way, there is a map from K cross some vector space to G, which makes it possible to speak of, sorry, I am trying to adapt my discourse to the passage of time. So G mod L contains a compact submanifold, namely just the cosets for the K. And away from this compact submanifold, G mod L is kind of flat because there is this map that there is this diffeomorphism between G mod L and the quotient of K cross some vector space by K cap L. So this this space S being a vector space, you can dilate things in there, and it gives you a notion of dilation in G mod L. And it gives you a notion of zooming in on the compact submanifold K mod K cap L that I was telling you about. So G mod L does not, you do not need to zoom in on the origin as you did for G mod K, but you need to zoom in on this compact submanifold. And the Mostov structure theorem I was telling you about makes this possible. So you can zoom in on a compact submanifold. And in the fiber, if you assume that you have found a contraction, you can at the same time zoom in on the submanifold here and deform in the fiber and see whether you obtain the realization for the lowest K-type that we are wishing to construct from pi. And it does work a bit miraculously. If you zoom in, the Dolbeault cohomology classes will start looking like classes of differential forms that are constants in the directions of Mostov. And you end up with a Dolbeault cohomology class for something that lives in K mod K cap L. And it turns out that it is exactly one of the realizations for the lowest K-type by the Borel-Walbot theorem. So it sort of miraculously works to adapt the idea of zooming in on the compact submanifold and using the contraction. It took me a long time to get this to work out. I needed Hodge theory and several ingredients that were not obvious to me, but in the end, it works perfectly. So now, sorry. So now we have reduced the contraction of any irreducible tempered representation, first to representations with real infinitesimal character, then to the representation V of L that was used to build the fiber of this bundle. But then it's a special kind of representation. It's a representation of a quasi-split group, and it can be embedded into a representation induced from a Levy subgroup, which is abelian. And in that setting, again, somehow miraculously, it's actually possible to build a realization as a space of sections of a bundle over G mod K with fiber exactly the lowest K type. So usually for real infinitesimal character representations, it's not possible to realize things as sections of a bundle over G mod K in any pleasant sense. But the Dolbeault step allows us to pass over to a special class of real infinitesimal character representations, for which we can take up exactly the same ideas as we used for the principal series and the discrete series. But I know that I'm running over time, so I won't be describing this in detail. It's really a combination of all the ideas I already used. But again, things get a bit messy if you have to estimate all convergences and guarantee everything. I'm running out of time, so I should stop with three takeaways. The first is that there is indeed a simple and natural bijection, but not an obvious bijection between the irreducible representations of G and G0. The second part of my talks says that it's possible to construct it geometrically, but as of our meeting, there is no construction that is completely simple, natural, and does not use the fine details. It's like building a beautiful, strolling through a beautiful garden in which you stop to look at every bench and every flower and see how miraculously it's arranged. but we have not been able yet to look at things from above and find a structural explanation for the deformation of representations, or even for the existence of this bijection, which was a mystery for such a long time. There are many promising ideas, many of them springing out from the work of Nigel and Ayal. There is this beautiful work with Joseph Bernstein to give conceptual framework for admissible representations. Ayal has been using this very efficiently. Shili New has been too. And on the C-star algebra side, the work of Nigel and Angel Roman, which is very recent and focused on C-star algebras, also gives very promising ideas. I think it's certainly not the end of the story. So thank you. I hope we meet next year in a different synod. Thank you. I think I'll stop here.
I see you found the correct picture.
Oh, it's just the first picture that I found on the internet.
Yep. Thank you very much. Are there any questions?
Yes. It's if I understand whatever I do understand from your construction correctly, it seems like this representation of G0 that you obtain is actually a quotient of some non-unitary representation, which is in some sense of the same size as that of G. For example, the same k-temp multiplicities. Is this correct? Is this?
Sorry, I couldn't hear the whole question. Could you repeat, please?
So the Bucky bijection is between the representations of G and representations of G0. But it's, if I understand correctly, the representations of G0 are in some sense much smaller, right? They have lower k-type multiplicities, for example. So do you obtain this representation of G0 as a quotient of some non-unitary representation?
Oh, that's very...
which has the same k-type multiplicities.
For tempered representations, what I've just described you is, in a sense, you almost obtain the representation of G0 as a kind of subspace of the representation of G you started from for tempered representations. So for G0, the unitary representations are always kind of smaller than the representations of G you start from. When you extend this to admissible representations that are possibly non-tempered, you have finite dimensional representations of G on one side that correspond to infinite dimensional representations of G0 on the other side. So in that case, it's certainly not possible to obtain the representation of G0 as a quotient of anything. But again, I understand very much less about the deformation of admissible representation. So for tempered representation, the answer is yes, and with a somehow subspace rather than quotient. And for admissible representation, the answer is no.
Thank you.
Thanks.
I have a question. You described the bijection between reducibles. Can one hope for functors?
I would love there to be a functor. I just have no idea. I would just love there to be a functor. It probably means understanding something about the behavior of Blancherel measures. And at this point, I have absolutely no idea, but perhaps people listening to us do have ideas about the behavior of Blancherel measures. But at this point, to my knowledge, it's an open question whether there is a functor at the level of, say, admissible GK modules that could make things. For GK modules, I should mention that the classification of admissible representation is due to Patrick Delorme, who is listening to us, and I think it was one of your very first papers in the 80s. So the category of admissible representation is known also for G0, so it would be very pleasant if there were a functor, I just don't know. Thanks.
Maybe I have a question.
Yes.
So what is the philosophical reason why it's the tempered unitary dual which matches with G0 hat? Is it because of this L2 spaces?
Oh, I really don't know. There is a bijection at the level of admissible duals, and it preserves temperedness on both sides. For G0, being tempered and being unitary is the same thing.
Yes.
So the reason why it's between the admissible duals and preserves temperedness rather than between the unitary duals, say that would have been wonderful, of course, but it's not true. I really have no idea.
But in some senses, temperedness is what shows up in L2 of G.
Yes.
And for L2 of G naught, everything is tempered, right?
Yes.
Yeah.
Right.
Okay. So in some sense, I mean, it's something between L2 of G, everything which shows up there,
Yes.
and something between L2 of G naught and everything that shows up there. So, yeah.
Yes, I do agree. And understanding more about this is probably equivalent to what I was saying earlier, understanding the behavior of Plancherel measures.
Yes. Then the question is whether you could do something for a homogeneous space.
I wonder. I don't know. I have never looked at this, but I would be very happy if there was something for homogeneous spaces.
Maybe the easiest thing is to start when H is a subgroup of K.
Yes.
I mean, there you should be able to see it. Yeah, some sort of.
Yes.
Okay, it was just a suggestion. Thanks.
Thanks for the suggestion.
Okay, if there are no more questions, then thank you very much again. Maybe we can try to give an applause or so if that works, and everybody has to unmute. Huh?
Then you have.
Okay. We can do this with symbols. Yeah. Okay, very good. Okay, so we'll have a break until 20 past, so that's about 12 minutes or so. Then we continue with Erik van der Ban.
Thanks, everybody.
Thanks.
Alexander, maybe I can still ask a question?
Yes.
Yeah. So, does any of these have some p-adic analog?
I've pondered this. It does not seem to have any p-adic analog. One possible reason is that it's so important for there to be this renormalizing maps which do not exist for p-adic groups, for p-adic groups.
If you want to come to the maximal compact, it's a p-adic. But if you just, or maybe I should ask it first of all in the real case. So if you have not the maximal compact, but some other, say, symmetric subgroup, so still can do the same deformation, yes? But then you get some group which is not semi-direct product of compact and linear, just semi-direct product of something and linear.
Yes.
Will something work?
Usually, no. You can take the trivial subgroup and do all this.
Okay.
In general, what kind of...
I take rank 1 symmetric pair, for example.
Yes, for that, it's a very good question. I don't know for a symmetric pair, but it's something worth looking at. I don't know. The phenomenon is so unexpected and so special that I don't know if there is anything to it, but it's certainly worth.
It's very unexpected that usually when you have a family that degenerates somewhere, you usually can do nothing with representations.
Usually it's the case. The most famous examples in physics are examples where things are bad.
Mm-hmm.
But there are certain examples where part of the dual goes over to the dual of the contracted group, but not everything. For the Poincaré Galilei contraction, that's exactly what happens. You start with a group that has interesting representations and infinite dimensional, not very interesting representations. And the interesting ones disappear, but the others are completely preserved, and you can do much the same thing as I did.
Poincaré Galilei is not just a special case of this?
No, Poincaré Galilei, you have a group that is not reductive and that also have an abelian factor. So it's
but if I just take SO31 And the generated, then I get SO3 semi-direct product with R3.
Let's take SO31. It's an example of what I said, of what I did. There it works.
And then you not just multiply both sides by R3 or something like this?
Well, if you multiply both sides by R4, the problem is that the product law is not the same in the two multiplications.
So it's actual different example. Yes, it's not a special case and not.
No, it's not special cases.
And there's just not two. The one representation theory is richer than the other.
Yes, the Poincaré one is richer than the Galilei one. In a sense, all the representations of the Poincaré group that have a physical meaning disappear, and all the others that correspond to particles with an imaginary mass, they do remain.
The non-interesting remains?
Yes.
Okay. Okay, I see. So it's very unique thing, yes. Thank you.
Thank you.
Can I ask a question?
Yes, of course.
Can this be made more explicit for at least some symmetric spaces? For example, Hermitian symmetric spaces?
Can the bijection be made more explicit?
Yeah, right.
Well, it all hinges on making Vaughan's theorem more explicit. If you can identify, given a representation of K, the real infinitesimal character representation that corresponds to it, then things are better. So for Hermitian symmetry, probably you can do something.
It was quite interesting. So
element.
What?
But in general, I've not tried this. I did just as Harish Chandra. I wrote down the example of SL2 and then everything. So, sorry, I don't have more on this, but the main point is describing the real infinitesimal character representations, and then if you have a concrete enough description of these ones, you have everything explicitly. But it's a challenging problem in general.
But maybe for holomorphic discrete series, one can see what.
Yes. I think so, because there the relationship between the lowest K type and the Harish Chandra parameter is completely explicit. You're completely right. For discrete series in general, and for holomorphic discrete series in particular, then it's quite explicit. Yes. Well, thanks everyone. If you don't have more questions, I'll just come back in a minute. But if you have any, feel free to ask them now or later. Thank you.
Thank you.
Hello. מישל, מישל, את יכולה לעזור לי רגע?
Let's see. Are you on?
אני לא שומע כלום. אני לא מבין אם זה התחיל.
זה עוד לא התחיל. אבל מצד שני כולם כן שומעים לך.
Okay, it's about time, so let's continue. So the second and last speaker of today is Erik van der Ban, who will speak about VA analysis of Whittaker functions.
Thank you very much, Job.
I will mute everybody again, but then you have to unmute yourself first, Erik. Otherwise, it will be a very boring talk.
I see.
Can you send the
Okay, can everyone hear me? Very good. So first of all, I would like to thank the organizers for inviting me to give this talk. I'm honored by it, but I must confess that I've never been as nervous in my study as I am now. But let's start. So as you can see, I try to imitate the zoom of the poster, but I do not have the skills of Job in tech. Oops. Our setting is as follows. G is a real reductive group. K is a maximal compact subgroup, and we fix an Iwasawa decomposition. So we fix a minimal parabolic subgroup with nilpotent radical N0. Chi is a unitary character of N0, and we assume that it is regular. So this is quite important for the subject. It turns out that there is also a theory for chi not regular, but this can basically be reduced to this theory. So regular means that if you take any simple root of A in R0, then the derivative of the character at the identity should be non-zero on the corresponding root space. We'll work with the following spaces of functions. First of all, the space of measurable functions on G that transform according to the character on the right by the action of n. So this is basically the space of measurable sections of the bundle that realizes the induced representation from chi, from R0 to G inducing chi. And then there is an obvious L2 space around. If you have a function, a measurable function, transforming according to chi, then its absolute value is invariant under R0 from the right. So it's really a function on G mod R0. And it makes perfect sense to speak of an L2 function. And so this is the space of L2 sections of the bundle. So we have a natural left regular, we have a natural left action, the left regular representation on this space, and that gives basically the unitarily induced representation up from R0 to G of the character chi. So this is unitary representation. So abstractly, since G is of type 1, we know that it has a direct integral decomposition into irreducible unitary representations of G appearing with certain multiplicities and with a certain Plancherel measure. And the question that I want to discuss today is the concrete realization of this Plancherel formula in the Whittaker context. And as we probably all know, there is work of Harris-Chandler that has remained unpublished for a long time. So there was an announcement in 1982, which had very precise statements, but the unpublished manuscripts of Harris-Chandler were not published for, well, almost 40 years. But fortunately, in 2018, the papers were put together, the different manuscripts were organized in such a way that one manuscript came out of it. And this has been done by Ganguly and Varadarajan it's part of the collected papers, volume 5, published with Springer. I think Ganguly and Varadarajan did a beautiful job. It's not quite reading like a paper because the organization, of course, cannot be that good, but one gets a lot from it. And one of the things that comes out of this paper is that the final step in reaching the Plancherel formula is not entirely clear. And this is what I want to discuss today, and I want to show how this step can be made through a new inversion theorem. I should also mention that there is an independent treatment of the subject by Wallach in his book Real Reductive Groups 2, but unfortunately, one of the basic lemmas contains an erroneous estimate, and that means that basically all material has to be reviewed in order to see what is affected. And there is a repair which has been addressed in a few preprints that have appeared under this archive number. But what I can say about it is that I have not been able to verify all statements there. So the discrete part of the decomposition, I think this is quite clear and well established, and this is due to Harris-Chandler and independently Wallach. So let me talk a little bit about this. So first of all, if we have a unitary irreducible representation of the group G, then we say that it appears discretely in L2 of G mod R0 with transformation behavior under the character. I'll call this from now on the space of Whittaker functions in order to be brief. It should appear discretely in there, so it should be realizable on a closed subspace. Then a theorem, which is quite remarkable due to both Harris-Chandler and Wallach, is that if pi appears discretely in the Whittaker space, then it must be a discrete series representation of the group itself. And this has the advantage that it gives a lot of information about the discrete series representations, in particular, the infinitesimal characters real and regular. We heard already about this in Alexander's talk, while the rank of K should be equal, the rank of G should be equal to the rank of K. So the rank condition should be satisfied. And this is very helpful if you want to separate tempered spectra in the Whittaker-Plancherel decomposition. So one of the things that is very important for the theory is to have a good space of Schwarz functions. And this was introduced by Harishchandra. I'll give the definition in a minute. First of all, rho is the usual half of the sum of the positive roots, and then associated with the positive roots of A in N0. And Z, or German Z, is the center of the universal enveloping algebra. Definition of the Schwarz space is as follows. It's the space of smooth sections of the line bundle, the smooth Whittaker functions, such that any derivative from the left satisfies a certain good estimate for growth behavior towards infinity. And since f is transforming in a unitary way on the right, n doesn't really play a role in this estimate. And it's natural to write this estimate in terms of an Iwasawa decomposition, of the Iwasawa decomposition. And the estimate is that independently of k, there should be an estimate in the, say, what we will call the radial direction or the A direction. And this is the expression that one would expect. And by the way, is my little hand visible for everyone? Okay, I'm relieved. So first of all, this appears as the inverse of a square root of a Jacobian associated to this decomposition. So that's quite natural for L2 theory. And then this says that it should be polynomially better than the estimates, than say the estimate that starts to be good for L2 theory. So now the strategy of the proof is reducing to k-finite functions, as we know very well from the case of a real reductive group or a symmetric space. And so we do this by fixing a finite dimensional unitary representation of k, tau in V tau, and working with the space of tau spherical Schwarz functions. So one way to look at it is you take the tensor product with V tau and you take the k invariance in this tensor product. So it means that if I have translation from the left by k, then it will become tau of k on the space V tau. And then we have the subspace of Schwarz functions that in addition are required to behave finitely under the action of the center of the universal enveloping algebra. So that means that f is annihilated by a co-finite ideal in this center. And that means that there are many differential equations satisfied, and they give a lot of information. Theorem, due to both Harishchandra and Waldek, if you look at this space of Z finite Schwarz-Whittaker functions, then it actually coincides with the space of tau spherical L2 functions on G mod and naught with behavior under chi that are in the part that comes from the discrete series matrix coefficients. So that come from representations that are discretely realized. And this space is finite dimensional. So that is very useful. What I'm going to do is I'm going to use some language of parabolic subgroups, and this looks like a list of notations, but it's not as awful as it looks, because I think quite a bit of notation is self-explanatory. But let's go through it. Sigma is the set of roots of A and G. Sigma plus is the choice of positive roots corresponding to N0. And then we have a set delta of simple roots. We have the little while group, the normalizer of A and K, modulo the centralizer of A and K, which of course is the while group of this root system. Then there is this minimal parabolic subgroup, which we will keep fixed and denote by P0. And then PA is the finite set of parabolic subgroups containing A. All these parabolic subgroups in this finite set are conjugate under the while group with the standard parabolic subgroups. The standard parabolic subgroups are those that are containing the minimal parabolic subgroup. Now, for a P parabolic subgroup, we will always write the Langdon's decomposition as MP, AP, NP. So like we saw in Alexandra's talk. We have a notion of associated parabolics if P and Q are two parabolics containing A, then we say that they're associate, denoted by a tilde, if and only if the corresponding split components are conjugate under the action of the little while group. If this is the case, it makes sense to define the following space of linear maps, which I'll call the while group homomorphisms. So these are the linear maps from AP to AQ. The linear maps for which there exists a while group element in the little while group that realizes this linear map by restricting to AP. Now, so as I said already, the discrete series is the representations of the discrete series are known, or at least they are exhausted by the discrete series of the group. And so the usual way towards a Plancherel formula is use these on levies and then induce up to parabolically to the group G. So to facilitate notation, I will use A2P for the A2 space of the Whittaker structures induced on the levy. So MP intersected N0 is the nilpotent radical of a minimal parabolic in here. We restrict the character to this intersection, and we restrict tau to the maximal compact subgroup intersected with MP. And so this will serve as a space for induction parameters, which I'll call the space of induced, of discrete induction parameters. Now, the idea is that the induction that is going to take place will cover all the discrete series representations that appear in this finite dimensional subspace. And that gives a very nice mechanism that I'm going to describe. I'm not going to give the definition of the so-called Whittaker integral, but let me just mention that there is a continuous spectral parameter which varies over the complexified dual of the split components. If the real part of lambda is P dominant, then one can build by the process of induction and starting with discrete induction data, one can build a so-called Whittaker integral. And this is going to be a Z finite, that's what A refers to, a Z finite and tempered version of Whittaker functions, the space of tempered Whittaker functions. So this is defined in a similar way as the Schwartz space, but instead of requiring polynomial decay, we allow polynomial increase. And the rest of the definition is the same. And we should observe that this Whittaker integral, that it is essentially a finite sum of generalized matrix coefficients of, on the one hand, k finite vectors, on the other hand, vectors that behave well under distributional vectors that behave well under the action of the nilpotent group N0 according to chi. And this is also formulated by making use of so-called Jacquet integrals. So you can view them as particular integrals on the space of the induced representation. And this is really the analog of the Eisenstein integral, which is, I think, the reason that Harris Chandler coined it the Whittaker integral. Now, we'll take a particular viewpoint. So I incorporated the psi here in the notation, but actually I want to decouple the psi from the Whittaker function, and I would rather see the Whittaker function as
Eric,
Yes.
I have a question.
Sure.
So you mentioned it in words, but then I think you didn't state it. I mean, the discrete spectrum of G is the same as the discrete spectrum of G mod N naught chi, the L2.
No, the discrete spectrum of G mod N naught chi is contained in the discrete spectrum of G.
It's not the same. I mean, without multiplicities, I mean.
I'm not sure about that. I think, well, in fact, I think it is, yeah, it is, I think it is the same.
Okay, then
but you have discrete, you have discrete series of all sorts of sizes.
Right.
And if you have a generic character, then, you know, the representations won't be generic. I mean, for split SP, you can see that, I suppose.
So
only the generic discrete series occur.
Aha. Thanks, Patrick.
Also, I have a remark. I don't think that the Whittaker integral goes in atom. These are not, if the parameter lambda is not unitary.
Oh, I'm sorry. You are very right. This is only true when, of course, this is not true. This is only true when lambda is imaginary. Okay. I'm very sorry. Yeah. Of course, this is not true. In a moment, we will see from the asymptotics that it is not true. So I'm contradicting myself. I was contradicting myself here. Thanks a lot for your remark. So yeah, this is true if we restrict lambda to the unitary part of the spectrum. So the real part should be 0.
Okay.
Yeah.
So I have, and maybe I ask then again, I mean, so let's take chi generic, then the discrete spectra of G and G mod N naught chi are the same, right? Is there an abstract?
No. Only the discrete series which have a Whittaker, which have a Whittaker functional occur. This is what is called generic discrete series.
Generic discrete series.
Generic discrete series has a special meaning.
So maybe we should discuss this afterwards.
Okay.
This is not really the subject of my talk.
Okay. Sorry.
And I'm really fairly new to this subject. So, okay, so bear with me, please. So the viewpoint will be that the Whittaker integral is going to be viewed as a, so not a tempered function, but a Z finite function on G naught mod N naught, behaving according to chi, but with values in a finite dimensional vector space, the space of all homomorphisms of the discrete induction parameter space to V tau, the representation space of K. Then there should be spherical behavior according to tau. And then, so I have incorporated the psi in the argument of the space of homomorphisms. And this depends homomorphically on lambda in the indicated region, which one immediately sees from the definition. I would like to give an example of the classical Whittaker functions. Could everybody please mute their microphone because I'm disturbed by an echo here. Thank you very much.
Sorry, I muted all. You have to unmute yourself, Eric.
That was the price that I had to pay. So take a character of SO2. Then, so it's quite bad, this echo. Okay, I have to live with it. So the Whittaker function it's basically determined by what it is in A, and then we can see A to the minus alpha, so into the minus positive roots as a variable, and then it becomes essentially a classical Whittaker function. Jot, is your microphone open?
No, it is not. I also hear the echo, and I have no idea where it comes from.
I think it's Roberto Miatello's mic, because his picture is flashing.
Let's just continue.
Sorry, Eric, you're muted again. But I think this echo is not going away, and I don't know why.
At 0. So that means that in this example of SL2R, this corresponds to the positive Weyl chamber. But in the other direction, so at infinity, there is actually an irregular singularity. And the asymptotic behavior of a basis of solutions, of the two-dimensional solution space of this ordinary differential equation is well known. And then one sees that there is a solution of very fast growth towards infinity and a solution of very fast decay. And of course, that means that if you take a linear combination of the two, then the generic linear combination will always have very fast growth because you do not see the very fast decay. And very fast growth means growing faster than any power of the variable. And here it means decreasing faster to 0 than any power of the variable, negative power of the variable. So that means that this Whittaker function that is picked out by representation theory is really a very special solution of the Whittaker ordinary differential equation. Theorem due to Nolan-Wallach is that if the Whittaker function, initially defined in the area that I described, extends to an entire holomorphic function of lambda with values in the space where the Whittaker function should come. Harris-Chandra doesn't have this result, but he obtains a meromorphic extension, which he shows is regular on the imaginary part of the spectrum. So this is enough for purposes of the Plancherel formula. And here comes my first result. One can show that these Whittaker functions satisfy uniformly tempered estimates. And by this, I mean the following. It is possible to, it's very similar to the uniformly tempered estimates for semi-simple symmetric spaces. One fixes this epsilon sufficiently small, and that means that there is a strip or a tubular neighborhood around the imaginary part of the spectrum by requiring the real part of lambda to be smaller than epsilon. And on that tubular neighborhood, one should have estimates of this type. For every left derivative, there should be constants such that this estimate holds, so that we allow tempered behavior in the variable lambda, the spectral variable. We allow tempered behavior in the space variable, so this is also part of it. And this factor turns out to be very useful. If lambda is imaginary, then it is 1. So then one has perfect tempered behavior. This has the advantage that we do not have, that we automatically get estimates if we take derivative with respect to the variable lambda. Because the function is holomorphic in lambda. So if you have estimates like this in subnorm, you will have, by the Cauchy inequalities, have estimates of derivatives. And this is a very useful aspect. Now, the proof of this result is, in some sense, it's similar to the proof that I gave many years ago for the minimal principal series, which was later generalized by Delorme in the context of semi-simple symmetric spaces. So one starts by deriving a functional equation for Jacquet integrals by using the idea of translation and projecting according to infinitesimal character. And something like this seems to happen in Wallach's book. So he gets this result, but I do not see the same type of functional equation that I'm interested in. This functional equation allows to shift the Whittaker area away from the original area of definition, where it is controlled by an integral. In the area of definition, it satisfies certain moderate, uniformly moderate estimates. And these are taken along with the translation by means of the functional equation. And then there is a Wallach there is a method of improving estimates of matrix coefficients along maximal parabolic subgroups using differential equations. And this method can be used with parameters, and then one obtains these sharp estimates. So it turns out that it's quite useful to work with a normalized Whittaker function. And here it will show up how wrong I was in stating the temperateness. So the Whittaker integral is a z finite function, and therefore it satisfies along the closure of the positive Weil chamber. It satisfies a system of differential equations with regular singularities at infinity. And that means that the behavior along this cone is very well understood. It's in terms of exponential functions that determine top order behavior. And the phenomenon that I mentioned for the classical Whittaker functions is also present here. In fact, the Whittaker functions decay more rapidly than any exponential if one stays away in this fashion from the closure of the positive Weil chamber. So there is rapid decay in these directions. And that means that if we're interested in the Planck-Schrell formula, we basically have to do asymptotics along standard parabolic subgroups. So a first lemma, which is basically the type of asymptotic behavior that everyone knows, for instance, from elementary spherical functions or matrix coefficients of k finite functions. Take a standard parabolic, take psi in the induced parameter space, take the real part of lambda in the positive Weil chamber in the split component of the parabolic, take m in MP, and let a tend to infinity in this chamber in the split components. Then the Whittaker function has top order behavior, which is given by this exponential. Psi occurs with a coefficient, which is the C function. And then there is M present describing the behavior transversal to a wall. And this CP of lambda is an endomorphism of the discrete parameter space. It's monomorphic in lambda, it's generically invertible, and it is regular for real part of lambda in the positive chamber. And what we will now do is we follow Harris-Chandra in giving this definition. We normalize the Whittaker function such that the new Whittaker function will have similar asymptotic behavior, but with the identity function here, so that psi appears without a coefficient. Now, this in the end will have the effect that we normalize away the Planck-Schrell measure. The Planck-Schrell measure will become the back measure because of this. Lemma: if you have two standard parabolics, P and Q, suppose that they are associated, so their split components are Weil group conjugates, then for any element in the set of Weil homomorphisms, one has a relation between the Whittaker integral for Q and the Whittaker integral for P. It transforms according to a C function. So I define now the C function by means of this equation. It's a uniquely determined meromorphic function of lambda in the complexified dual of the split components. Now, theorem, the Marcelberg relations are valid here, and this is due to Harris-Chandra. If you consider any of these coefficients, then they will satisfy an equation like this, and an equation like this because of holomorphy. So here we take the Hermitian conjugate. So this is a holomorphic expression. So this identity is completely determined by what it does for lambda imaginary. And then, of course, this is equal to lambda. And then one sees that this map is unitary. So for lambda imaginary, this map is unitary. And of course, these C functions arise in the description of the asymptotic behavior of the Whittaker integrals. But I formulated it here in this way because I do not want to tire you with a notation that would become rather heavy. Now, if you make these unitary, then from the asymptotic behavior of the new normalized Whittaker function, so you have potentially introduced singularities here because you have divided by a meromorphic function. But because of the unitary behavior of this function, this actually is still regular on IAP star. Now, to define the Fourier transform, what I have to do is I have to test with something like a complex conjugate of this Whittaker integral. So what one can do is one can take the Hermitian conjugates, spectral parameter minus lambda bar, and this defines the so-called dual Whittaker function. And the Fourier transform can then be defined by integrating a Schwartz function. So now, fortunately, I've written lambda is imaginary. So that means that this Whittaker function is a tempered function. So if you have a Schwartz function, then you can test the Whittaker function, the Whittaker integral with this Schwartz function, and this will give an element. F of x has values in the space V tau. This Whittaker function has values in the space A2P, so you are left with something in the discrete parameter space. So the Fourier transform assigns to F a discrete induction parameter. Now, theorem, this Fourier transform maps the Schwartz space continuous linearly into the Euclidean Schwartz space with the proper coefficients. And Harris-Chandra doesn't prove this. He proves this only for the Fourier transform restricted to the smooth functions with compact support here. Compact support here, of course, should be understood modulo and naught. And the proof is almost an immediate consequence of the uniformly tempered estimates that I formulated a few slides ago. Let me see, how am I doing with time?
Oh, yeah, 25 minutes and a bit, yeah.
Sorry Job, ik verstond je niet. Sorry, Job, I'm sorry, I didn't understand you.
25 minutes at least, yeah.
25 minutes, thank you very much. So we want to have a Fourier inversion theorem. So what we also need is not only decomposing a function, but also composing a function by forming wave packets. And so we define the following type of operator. Again, for P, a standard parabolic subgroup. For psi, an appropriate. Well, now an induction parameter which depends on the continuous spectral variable in a Schwartz way. And what we then take is the superposition of the Whittaker integrals with respect to lambda. This is perfect because of the perfectly defined because of the uniformly tempered estimates for the Whittaker integrals. And so one can show that this actually defines a smooth function on G mod N0, but in fact, it turns out that this transformation is continuous linear. It maps into the Schwartz space, and it is a continuous linear map from the Schwartz amplitude space to the Schwartz space of Whittaker functions. And Harris-Chandra again only proves this for the wave packet transform restricted to the smooth compactly supported functions with values in the proper parameter space. Now the proof of this is again, it is similar to the proof of the similar result for semi-simple symmetric spaces. The proof requires the uniformly tempered estimates. So Harris-Chandra didn't have this, so he had a problem of defining this on the level of the Schwartz space, apparently. There is a theory of the constant term needed with parameter. There is very little information about this in Harris-Chandra's manuscripts, but if you read his manuscript Harmonic Analysis 1 and 2 on the group carefully, then there is a suggestion how to do this. And you can also read Carmona's work on the constant term in the case of reductive symmetric space. So there is a very good theory of the constant term with parameter, which deals with the asymptotics. And then there is also a theory of type 2 lambda. 2 lambda would be the version of Harris-Chandra. 2 holomorphic lambda would be a version with holomorphic parameter dependence, which makes things easier to achieve. And this is very similar to previous joint work of myself with Carmona and Delorme for reductive symmetric spaces. So what is apparent here, and people informed about reductive symmetric spaces will immediately note the enormous, that the appearance of the theory is very similar. So I now come to the Plancherel formula. If P and Q are standard parabolics, so containing P naught, and they are associated, so their split components are Borel group conjugates, then from the Maas-Selberg relations, one reads off that actually the norms of the Fourier transforms are equal for different parabolics P and Q. So and the reason is that this is defined by superposition of a Whittaker function. The Whittaker function has these functional equations by the Maas, and then by the Maas-Selberg relations, these functional equations are given by unitary operators, and therefore there is equality of norms. That's the idea. And then the Plancherel's identity, which Harris-Chandra formulates, says with a suitable normalization of the Lebesgue measures, one has that the L2 norm squared of a Whittaker function is a sum over L2 norm squareds of Fourier transforms, and you have to sum over classes of associateness of standard parabolics. And as I said, the outcome of this norm would be the same for different associated parabolics. But the Plancherel identity is not complete because it's only proven for F in a finite span of, in the linear span, I mean, of the wave packets. So look, take the Schwarz space, take all possible wave packets with psi, a Schwarz function, or actually Harris-Chandra does it for a smooth continuously supported function. Take standard parabolics and take all wave packets and take the linear span of that space in the Schwarz space. Then on that space, one has the Plancherel identity. But of course, what one really needs is that this space of wave packets should be dense in L2 to get the full Plancherel formula in L2 sense. And the proof, I have not been able to find the proof of that statement in the book. There is one reasoning that goes in the direction, but then there was a statement that said it is easy to see that, and I couldn't see it at all. In fact, I could only see it after proving the Plancherel formula. So that was not very helpful. And yeah, so this is what I can say about the state of Harris-Chandra's work. What is true is that the authors Ganguly and Varadarajan make the same statements, that they cannot find the proof of this, they cannot find the completion of the proof of the Plancherel formula. But they say presumably it is a not too difficult consequence of the material in preceding paragraphs. I've gone through it and I don't see how those things could give it. But of course, this could be my limitations. So I want to make this reservation, but then I do have the theorem. Yes, this is true. More precisely, one can in fact, for a Schwarz function in the Whittaker space, immediately prove this inversion formula. And of course, this gives it, because it shows that actually the span of the wave packets is all. So the strategy for this final step is to use a Paley-Wiener shift argument and residue calculus, as we know from the theory of the symmetric spaces. So this is previous joint work of myself with Henrik Sliefkool, who is also listening. Hello, Henrik. it all starts with just using the Whittaker integral of a minimal parabolic. And in fact, I want to use now a Whittaker integral which is non-normalized. So that means that it is everywhere holomorphic. We know that this function is finite under the center of the universal enveloping algebra, so therefore it satisfies a cofinite system of differential equations with regular singularities in the direction of the positive Wild chamber. I said that already. And then, because of this, one can show that it has an expansion at infinity of this type, where there is a decomposition over the Wild group, and where these functions are basically what we know as the Harris-Chandra series. For spherical function, we know these functions as the functions given by the Harris-Chandra series. So you can do a similar thing here. This Whittaker plus is this time, and this is different in the theory. It's a globally defined functions on G with values in the dual induction parameter space. It's meromorphic in lambda, so you have to pay something, but it's given by a simple series expansion of this type. And the series expansion is convergent for all A in A, so you don't have to restrict to the positive chamber. It's really globally valid, but of course it only gives growth, only gives information about the asymptotic growth in the direction of the positive Wild chamber. Now these coefficients are meromorphic, and they are determined once you require that they are the natural coefficient at 0, which is evaluation of psi at the identity element. And then if one sums over the Wild group, it means that you will see a to the s lambda minus rho show up as exponents, and the C functions show up. So these are the unnormalized C functions. So that means that I should normalize back the C functions that I introduced to these C functions by the obvious formula. And then one gets this formula. So these describe now the asymptotic behavior of this WH, of this Whittaker function towards infinity in the positive Wild chamber. The key theorem now, which is going to do the work for us, is that if you start with any smooth compactly supported function in Whittaker space, then there is a nice inversion theorem. F is given by an integral transform applied to F, and this integral transform is given in this way. First of all, we take the Fourier transform with respect to the Whittaker integral for the minimal parabolic. So P is P naught all the time now. We take this minimal, so we take this WH plus function, so this one Harris-Chandra series without the C function, and the statement is that the statement is that I made a mistake here, that there should be the normalized Fourier transform should be here. I'm sorry. So there should, oh, but the definition was as a normalized transform. I'm sorry, this is all fine. And so what we do is we integrate, so this is a function which depends meromorphically on the parameter lambda. We integrate over the imaginary part of the split, dual of the split component, shift it in the P anti-dominant direction, so the P bar dominant direction. And the idea is that if you shift far enough, you won't encounter singularities anymore, so then the integral becomes stable. It's not dependent on eta anymore. But you have to go somewhere because this function will be a meromorphic function with singularities, so you can't just take the integral everywhere. Now, yeah, one remark one can make is that you take this superposition, but you, in some sense, you go outside the realm of our Whittaker functions that have controlled asymptotic behavior in the other directions than the positive Wild chamber. Now, this is very similar to what happens in the case of a reductive symmetric space. There, the problem is that these Harris-Chandra series, they do not converge anymore on the walls of the positive chamber. And so what you get is you work with a function here that is not globally defined on the group. So here the situation is different. The function is globally defined on the group, but the asymptotic behavior in different directions from the positive Weil chamber is very bad. But it is a kind of miracle that by taking the superposition, you get rid of this. Okay, I want to briefly sketch some ideas of the proof. So first, we consider this integral transform as a transform from smooth, compactly supported functions to smooth functions of Whittaker type. And then the idea is that we are going to shift eta back to 0 in order to compare with the minimal spectrum. But of course, we cannot do that because we will meet singularities. But the singularities can be cancelled out by using a particular differential operator of the center of the universal enveloping algebra. One uses a differential operator whose symbol will cancel out, which will depend on lambda, and we will cancel out the singularities here. And so that means that the shift can be made, and then it can be rewritten as D composed with the wave packet transform composed with the Fourier transform. Now, a second idea is that by making a Pereira shift in the p-bar dominant direction, you can show that actually this operator is support preserving, this operator dt eta is support preserving, except for that it can be smeared out under k. But that means that you can take a radial component relative to k and n0, and then you get a radial operator, which is support preserving as an operator from smooth compactly supported functions on A to smooth functions on A, and therefore it's a differential operator. This differential operator, this radial part, commutes with the radial parts of the operators from the center. And that means that basically this differential operator satisfies itself a lot of differential equations, that is, the coefficients do. And so it turns out that it is completely determined by its top order asymptotic behavior. And this top order asymptotic behavior can be determined through Euclidean Fourier analysis. Then one finds that this operator has the same top order operator as D itself. And then these operators have to be the same on the smooth compactly supported functions. And now we apply, as in the case of semi-simple symmetric spaces, Holmgren's uniqueness theorem for analytic partial differential operators. Suppose that we have a compactly supported function, and suppose that d of t eta of f is df. Then it means that d of the difference is 0. But this operator was support preserving, so it's compactly supported. This function is compactly supported, so t eta f minus f is compactly supported. And if an analytic operator with control over the characteristic varieties kills a smooth compactly supported function, then the function actually has to be 0. So it's a kind of ellipticity argument in the analytic context. And so, and this completes the proof because we had to show that t eta of f is f. Oh. Now, the next step is that if you have a compactly supported smooth function of Whittaker type, then it is given by this formula. And now the idea is that you can shift eta back to 0 and pick up the residues, and now you care about them and you start organizing them in a scheme that Henrik and I developed for semi-simple symmetric spaces. And the organizational principle is governed by certain weights. So what happens is that you pick up residues along the singularities of these functions are along root hyperplanes or shifted root hyperplanes. You pick them up, you move further in these planes, you pick up lower dimensional residues, etc., etc. So this is quite complicated combinatorics, but fortunately it behaves well under induction. And in this way, it is possible to show that fx is actually given as a sum over the standard parabolics that take care, the associated root hyperplanes take care of the root hyperplanes appearing here or in the singularities. And then so when a certain coefficients, where this comes from a counting argument, and this comes from an arbitrarily chosen weight function, which distributed weight to parabolic subgroups in an associateness class. And there is a certain transformation that can be given as a kernel integral where the integration is first over y, so it's a kind of Fourier transform, so it's an integral transform kernel. And the outcoming variable is x. The input variables are lambda and y. And here it is good to remark that the integral cannot be taken immediately over the imaginary dual of the split component, because it is not certain that these operators are singularity free there, or these kernels are singularity free there. So one takes epsilon q small, but sufficiently close to 0, so that no further singularities will be met, but not all the way to 0. And then the theorem is that these kernels can actually be identified by the kernels of with what did I write down here? I wrote down something. No, it's okay. I'm sorry. It's late. So what I wrote down here is if you write down the Fourier transform, it uses this kernel, and then it's followed by a wave packet transform. It's given by this kernel, and you find in this way you find the kernel of this transformation. And it turns out that one can identify the kernels that are picked up here with the kernels of the wave packet transform after Fourier transform. And the identification can be made by looking at by showing temperedness of the kernels, which is okay. And then by looking at just one exponent, the identification can be made, since we have the Maas-Selberg relations. But then we know that actually this kernel does not have singularities for lambda imaginary, so then one can take the limit for EQ going to 0. And this gives one the Plancherel formula. And of course, one has these, so this shows that this is a sum over all standard parabolics, and TQ measures the weight by which they count in this residue scheme. So these coefficients appear because of counting arguments and because of a different choice of measures, which has to be worked out in detail, of course, but which is in the other formula was given up to choice of measures. Okay. Now, if you are familiar with this subject and you have seen the arguments, then you will start immediately to wonder, is there a Paley-Wiener theorem around? Because Paley-Wiener arguments play such an important role. And the answer is yes, there is. And I think I still have enough time to describe it. So surprisingly, the Paley-Wiener theorem, or maybe not surprisingly, is not about functions with compact support. It's functions, Schwartz functions of Whittaker type that are cone supported, and by this I mean that the support should be contained of the function. If you look on the A component, so we have, of course, that the Whittaker function, the support will be left invariant under K and right invariant under N0. So one is left with a description of support on A, and I do it in the Lie algebra of A, and the support should be contained in a cone of this type, where H0 is an arbitrary element, and minus A++ is the negative dual cone of the positive chamber. So it's generated by the root vectors. And of course, this cone could be here or it could be there, but it should be somewhere. And such a function will be called cone supported. And then the lemma says, oh, actually, this is an interesting space because it is not a space of compactly supported functions, but it is very close to compactly supported, because if you take any derivative from the left and you look at the growth behavior along A, then it will be of this type. This growth behavior is, of course, taken care of in these directions because of the support behavior, because of the supports. Here, the asymptotic behavior is obviously 0, But in the other directions, outside the positive chamber, the direction is still faster than any negative exponential. So that means that it's more a function of the Wallach-Schwarz type. So it's a function of a Wallach-Schwarz type, which has support inside such a cone. And then the Peduino theorem says, oops, that was too early. The Peduino theorem says that take a minimal parabolic, take the unnormalized Fourier transform. So that means that we take the Fourier transform with respect to the unnormalized Whittaker function. Then it's injective on this space. And the image is given as a Peduino space, which is defined to be a space of holomorphic functions phi on the complex dualized split component with values in the discrete parameter space. This was a finite dimensional space, satisfying, first of all, certain estimates of Peduino type in restricting directions corresponding to the dual of this cone, so corresponding to these directions. And then also the analogs of the relations of Arthur Campoli type. So any relation of a particular type between Whittaker functions, derivatives of Whittaker functions with respect to the spectral parameters in different points should be seen in the function in this Peduino space. So this was what I had to tell you. Thank you very much for your attention.
Okay, thank you very much. Are there any questions?
I have a question actually for Patrick, if I may. Patrick?
You have to unmute yourself, Patrick.
Oh,
okay.
Okay. Oh, thank you. I have a question for you. You have this Peduino theorem for the p-adic Whittaker version of the Peduino theorem.
Yes. I was looking to this to remind me what was the
right.
theorem.
So my question is, I don't understand the p-adic language very well, but I would like to know if there is an analogy between this Peduino theorem and
I think the p-adic version is better.
Aha.
No, because only intertwining integrals. So this is given in terms of cuspidal things, not in terms of discrete series, but cuspidal thing, and then the intertwining conditions are only given by intertwining integrals. So it's okay. So, but it was the same for the group case by the theorem of Bernstein and Eiermann, that the symmetry relation are only given in terms of Eisenstein, of intertwining integrals.
Okay. Okay, thank you.
Okay, but and I was looking to the proof, and okay, this is slightly different, and the proof of the Plancherel theorem is quite close to the proof of the Plancherel theorem of Harishchandra. So for the p-adic groups also, but I had no time during your lecture to reread everything.
I'm happy I didn't give you the time.
Thank you. Thank you. Thank you.
Are there any other questions?
Yes. No, then I just wanted to thank the speakers. So maybe you had done more work than we as organizers. So you really took a lot of effort, both of you. One could see that. And I wanted to say that I really appreciated that. Thank you.
Thank you.
Thank you.
Thank you very much.
Can I still ask questions? Or,
Sure. Oh, yes.
Oh, okay. So, hi. Yes. So for the people who are sort of more expert in automorphic forms, so if something is in the cuspidal automorphic representation, then does the local part, what relation does that, the local part of such a representation have to do with the Whittaker-Plancherel measure?
I'm not sure I understand your question. What I didn't mention here is that there is a theorem of Harris-Chandra that says that there is a notion of cusp form here.
Yes.
And so there are these parabolic descent integrals. So there are these cusp form conditions. If you impose that condition on a tall spherical Schwartz function in the Whittaker space, that these integrals are all vanishing, that you have a cusp form, then actually that space of cusp forms is identical to the space of discrete series Whittaker functions. So let us maybe go back to the definition of this space here.
Yes.
So this space is, by a theorem of Harris-Chandra, is equal to that space. But there is another theorem of Harris-Chandra, and that is that the space of cusp forms in here is identical to this space. And curiously enough, he uses the theory of the group for that. He uses the result of the group, and then he applies an averaging operator, integrating over N0 to get functions that transform according to chi. And this is how he proves it. And it is quite clear that the idea of his work is to use his philosophy. And the philosophy is that this should be enough for the completeness matter. The problem is, if you look at the proof in the case of the group, what you really need is that the Fourier transform and the wave packet transform live on the level of the Schwartz space. So, and he only developed it on the level of smooth compactly supported functions. So there is a kind of misfit. And this is my reason that I do not see how to do without those tools. Did I answer your question a bit?
No, but you explained very interesting things. But you explained very interesting things.
Okay, so if there are no more questions, then let me just say that we will continue tomorrow then.
There is another question?
Okay.
Now I want Saki to repeat his question. He was asking something about automorphic functions or representations. What exactly was your question?
You're asking me, Andrea?
Yeah.
Yeah. Oh, so no. Just so if I have some sort of cuspidal automorphic representation, then what does the local part, say at infinity or something, have to do with the Plancherel formula? I mean, is it in the support? Because there's some interest in how large or what sort of orbits could occur as local parts of automorphic representation. Just wanted to understand.
No, but it might be zero.
Yeah. No, if it's supercuspidal. You're asking about supercuspidal.
No.
Cuspidal automorphic representation But it's it might be Whittaker part might be 0.
Whittaker part might be 0. Okay.
Yeah.
So the plunge. Okay. So this may not. This doesn't capture. Yeah.
No.
Okay. This does not completely capture that. Okay.
Okay.
Thank you. Thank you, Joseph.